Hello, my name is Martin King, and I'm going to be introducing our talk today on laser applications for the 21st century. So, first things first, we shall look at what a laser is. Now, you're probably all familiar with lasers. You get them in CD players, DVD players, Blu-ray players now, and little things such as laser pointers. Now, laser itself is an acronym which stands for light amplification by stimulated emission of radiation. Now, laser light has unique properties. Two of these being that it's monodirectional, meaning that we get a nice, we can have a nice narrow beam which doesn't spread out too much in one particular direction. Also, it's also a monochromatic. It can also be a monochromatic beam, which means that it occupies a very narrow range of the electromagnetic spectrum, which we'll have a quick look at now. Now, as you can see, it's the part of the spectrum that we see with our eyes is a very small part of the whole spectrum. And for example, a green laser would occupy a very narrow band of the visible light spectrum. And if we go up in the electromagnetic spectrum, we get infrared and radar and microwaves. And if we go down, we get things such as ultraviolet rays and X-rays, which you'll probably be familiar with if you've ever broken a bone and had to go to hospital. Now, another property is the intensity. Now, as you focus a laser beam onto a smaller area, it becomes more intense. So a laser with the same power focused at the narrower area will have a much higher intensity than a laser with the same power focused onto a much larger area. So the lasers applications we're looking at cover a very wide range of intensities, from gold nanocluster fluorescence to Raman Vex cells up to fusion and X-ray sources. And we'll start off with gold nanocluster fluorescence, and I'll pass you over to Martin Keating, who will talk to you about that. Thank you.
Hi, I'm Martin Keating, and today I'm going to talk to you about fluorescence of gold nanoclusters. Now, my particular area of research uses lasers, mostly UV lasers, in the milliwatt range. Down here we see gold nanocluster fluorescence. Now, first of all, what is fluorescence? Well, fluorescence is when an electron which has been excited to a higher energy level, if you look at the representation of this atom, returns to a lower energy level. So if you can imagine this atom becoming excited, and an electron will perhaps jump from the n equals 2 energy level to the n equals 3 energy level, and on returning back to its original energy level, the n equals 2, it will emit a photon. So that essentially is what fluorescence is. And what is a gold nanocluster? Well, by definition, a nanocluster, doesn't have to be a gold nanocluster, a nanocluster is on the borderline of about 10 nanometers or less. So 1 nanometer is an extremely small unit of distance. It's that point followed by 8 zeros, 1 meters, which is exceedingly small, very, very much smaller than a human cell. And we can use that to our advantage in certain medical applications. So what happens when you mix a gold nanocluster fluoresce? Well, we can excite the gold nanocluster by a UV laser, and what will happen is electrons will become excited to higher energy levels, and as I said, returning to those lower energy levels, photons of light will be emitted. Now, the different sizes of energy jumps will create photons of different energies or photons of different frequencies. And also, we can tune the nanoclusters by their size. So for example, if we decrease the size of the gold nanocluster, we can prompt the nanocluster to emit photons of increasing energy. It just so happens in my area of research, I'll be using nanoclusters round about slightly less than 2 nanometers, probably about 1.5 nanometers. And that just so happens to emit visible light in the red part of the spectrum, which is really good because that helps cut down background fluorescence. That's fluorescence that we don't want when we're going to use these nanoclusters in medical applications. Now, incidentally, the reason that gold has been chosen is that it's relatively non-toxic. So obviously we want that when we look at use nanoclusters for bioimaging or biolabeling of parts of cells, for example. And what can happen is the nanoclusters, because they're so small, they can move quite freely through cells, relatively unhindered, and because they're non-toxic, they don't have a harmful effect on the cell. And this can be used in, as I said, biolabeling, bioimaging. It can be used to evaluate the effectiveness of drug and gene therapies as well, for example. So now I'll hand you over to Daniele, who'll talk about laser applications in his area of research.
Hello everybody, I'm Daniele. I'm going to talk about innovative laser called Raman Vexel. As you can see from this table, this laser works at higher intensity range than the previous one. We are around 1 gigawatt per meter square. So where Raman Vexel? The aim is to build a new laser which works at frequencies that we are not able to reach with other lasers. So basically what I want to do is to build a sort of magic box which is able to change the frequency or the color, if you prefer, of a laser beam. So thanks to this new technology, we will be able to build new devices which can be employed in medicine and telecommunication. So what's inside the magic box? The Raman Vexel, obviously. And as you can see, it's a quite complex system. So we have a pump laser, which is a random laser, it doesn't matter which one, which generates a laser beam which is focused on SDL. This SDL is a quite complex object. Don't be scared, just keep in mind that this SDL lowers the frequency operation of a laser beam. Then we have two mirrors, which are quite important because changing the distance between them, we can manage the beam spot size and the light intensity. Then we have a Raman crystal and another mirror. So all this is a Raman Vexel. The part from the pump laser to the mirror 2 is called Vexel, and we have a picture about. Then this Vexel generates a pump beam, a laser beam. This laser is focused on a Raman crystal, which changes the frequency operation of the laser using the Raman effect. So the output laser will have a different color or a different frequency, if you prefer, of the laser beam generated by the Vexel. Thank you.
Hello, I'm Grace Manahan, and I'm going to talk to you about the applications of lasers for higher energy. So for energy greater than 10 to the 18, we can classify this as high power lasers, and there are a lot of applications, and one of these is using this laser as a source to generate X-ray. So one example is this future X-ray source, which we called Alpha X. Alpha X simply stands for Advanced Laser Plasma High Energy Accelerator towards X-ray. This may seem complicated to you, but actually you only need 3 requirements and 3 steps to have this system. So what do we need? First, we need a high power femtosecond laser system. So what do we mean by femtosecond laser? You only need to put 14 zeros before 1 second. And then the next step is you need a fully ionized gas, which we call plasma. And it's really nice to put it into a capillary tube. So to give you an idea, this capillary tube, it has a length of a few centimeter and a few millimeter wide. And the next requirement is to have an undulator, which is simply an array of alternating magnets. So what do we need to do? So first, we need to focus this pulse into the plasma inside the capillary. And what do we have? We will get, upon the interaction, we will get a very energetic electrons. When we mean energetic electrons, it means that the energy of the electrons can reach really very high, such that it can travel into the speed of light, which is approximately 3 times 10 to the 8 meters per second. And after this, we get these very energetic electrons wiggle rapidly into the undulator. And the result of this is actually a radiation source which can range from IR to visible. And if you have a very high energy, you can have a radiation source that can range into X-rays. So if we go back to this picture, so this is where the femtosecond laser, and it interacts inside this chamber, the plasma, and beside this blue side is the insulator, where we can have the radiation source. And now I'm going to hand you to Ross that will talk about another application of high power lasers.
Hi everyone, I'm going to talk to you today about fusion using lasers. But first of all, I'll explain what fusion is. It's a nuclear reaction, much like fission, where you split up the nucleus, but here we're trying to force two nuclei together under high temperatures and a lot of pressure. So we overcome the Coulomb repulsion between the two nuclei. When you overcome the Coulomb repulsion, you release a lot of energy, and on Earth we can use that for power plants or anything of that sort. But in the sun, use that to generate light and heat, but it's gravitational pressure that creates fusion in the sun. So on Earth we do a similar process, either using magnetic fields like they do for magnetic confinement fusion, or we can use lasers, high intensity lasers using inertial confinement fusion. And at Strathclyde we look at a new concept of fusion called fast ignition, where we take a fuel pellet composed of deuterium and tritium and we fire lasers at it, and the lasers induce a lot of pressure on the surface of the fuel pellet and compress it down. The fast ignition concept uses a second, even higher intensity laser to punch through the compressed fuel pellet into the core, and it heats up the electrons, and that means you can achieve fusion with relatively low energies. So as I say, we use intense lasers to compress deuterium and tritium fuel. When it's compressed enough, the electrons inside the fuel pellet have enough energy to force the nuclei together and create fusion. And the research interest at Strathclyde is how the electrons move from the outside of the fuel pellet to the inside. If they diverge, that means we lose energy, and it means we need a more intense laser. What we're trying to do is make them not diverge, not filament, go straight to the core and get ignition. And hopefully that will work, because we'll have a new energy source on the Earth, which will generate much more energy than oil or coal or gas, and there's no CO2 emissions from it.
Well, as you've seen, at Strathclyde we are currently looking at a wide range of laser applications, from gold nanocluster fluorescence, which can have applications in medicine. We have the Raman Vex cells, which produce new frequencies which can be used in telecommunications. We have the Alpha X, which can be used as a new X-ray source. And we have the fast ignition fusion, which can hopefully lead to a new clean energy source. And I'd like to thank you all for your time.